Hey everybody, welcome back to Andy making a NES ROM from scratch. As someone in chat has already astutely asserted, I am indeed around 30 seconds late, but I'll just have to push through that. Welcome, Princess Rega. Anyway, so we're going to continue working on the NES test. It's been around a week since I've last streamed and since I've last done something like this, so gonna have to take a while to get my head back into it and then see where we can go. Alright, so I'm just going to start with looking at this pull request that Dan Tupp has opened, which is talking about using the NES test, which we kind of went over last week, but never really got into the full detail of because I didn't fully understand what was going on. So what he was saying was it's a ROM where you load the ROM and put the PC at 0x0C. I didn't really understand what was going on there. So he has replied with another comment, and he said, here's the info. Basically, you just need to load the bytes starting at offset 0x0010 and map that into ROM at some location. So what we're actually doing is going to be loading this ROM, which we knew was what we're going to have to do eventually anyway, was load it into the actual memory map of where the CPU can access, and then we're going to start the execution at that point. And this means that it's just all our memory offsets are going to have to be done like that. So he's posted some loading code here saying, here's what needs to be done. Yeah, let's just do that. So he writes it to 0x80 and 0xC0 and then logs some stuff. It's worth getting working sooner rather than later. Cool. Alright, let's do that then. Just as a side note, Dan Tupp has also posted some cool stuff on writing a Chip 8 emulator in C#, which seems pretty cool, and written a nice blog post about that. So if you're interested in doing some emulating work, I would recommend reading this post, building a Chip 8 interpreter in C#, and also, yeah, just messing around and creating a Chip 8 emulator. Alright, well in that case, let's get going. So let's go back to PyCharm and try to remember where we left off. So basically, let's open the CPU. So for those of you that haven't been here before, basically what we're doing is emulating a NES fully. And so we started from scratch and we're doing it all in Python 3. So where are we up to? Basically we've got some simulated RAM, we've got some instructions that we can interpret. We're still working on the CPU, so we're still working on creating more instructions that we can read in and figure out what they are, but we've been working on getting all the different types of addressing going and some of the different instructions as well. So that's pretty cool. Alright, what do we want to be doing now is loading in this NES test, which is just a list of all the instructions that the 6502 CPU on the NES can have, as well as, you know, test that they're all working correctly. So we're just going to load that in and start checking that we've implemented our instructions correctly and that kind of jazz. Some of them which I know we haven't. Alright. So basically what we're saying is that the ROM is going to get loaded in 4x0 to 0x0. So basically the ROM is actually going to get loaded in to where? So this is the cartridge expansion ROM, and this is the program ROM. So I actually think that instead of going from 4020 to 0xFFF, we probably just want this to go, because that's just the registers. We want this to go from here to here. So we want this to go from C00 4000, yeah, and it's duplicated. Right, so basically what we're saying is when we're loading in the ROM, we actually want the memory in the ROM to be copied to those memory locations we just saw there. So let's do that. Let's go to our main and let's see how we load in a ROM. So we're going to create a ROM bytes. We're going to say it has a header size of 16, which is actually just 0x10 in hexadecimal. Number of program blocks, whatever. And so we're going to know what the program bytes are. So what we actually want to do is load these programming bytes into memory. And we do that by making it a memory owner that's going to start at here and end at here. The ROM is the ROM, and the PC reg is going to be the header size. Right, so I think we actually want the PC reg to start at 0xC000 as always. Alright. So the PC reg has got to start there, and we've got to load in those instructions. So load the ROM program instructions into memory. So we want to load them into memory. So, and we've actually got what those program instructions are stored in the ROM PRG bytes, which is here. So let's load these into memory. Now the other one is the memory start location of this 4020 to 0xFFF. And that's the end of our memory. Which is here. So we're saying all of this is cartridge, when in reality we probably just want it to be 8000 and C. So let's make it start at 0x8000. Let's make it go all the way up to, what's one less than that? BFFF. And we actually want it to just return the program bytes. I believe. Return self.rom. So we want to get the instruction at the first thing. So let's return the PRG bytes. And then when we get. Alright. Now actually, I believe that we should put this in memory owner. This is where it's all going to start getting a little bit difficult, because I haven't done any of this for a while. But anyway, so what's a memory owner mix-in? It has a start location and an end location. It can get the memory, it can get some values there, and it can set. This is what we want to actually do for the ROM. We want to make a ROM inherit from the memory owner mix-in. And we want its memory to start at 0x8, and we want it to end at 0xBF. Now, in reality, we actually want this to end at FFF, and we just want to duplicate, if we look at the memory map, from 8 to BFF and from C to FFF are both PRG ROMs, and we're just going to duplicate the copying the code into both. Alright, so let's do that. So here we can, when we're loading it in, we can figure out what kind of configuration the ROM is in. But for now, we just want to pull out what are the program bytes. So what is the actual code of the ROM? And then when we get the memory, we just want to return self.programming bytes. Yeah. And then this get comes for free with this memory owner mix-in. And the ROM is actually just, we'll pass in some, we'll just append the ROM to the memory owners. So every time we run a ROM, we're going to add it to the memory owners. Data pen the ROM. And we're going to unload the old ROM. So self.memory owners dot remove self.rom. Now potentially self.rom might be num, so if it's not num, we want to remove it. Then we want to set the new ROM, and we want to load it into the memory owners. Cool. Now this should disappear because we don't need it, because it's now going to be in the memory owners. Running, so we want to, okay, so now when we're running, we want to actually get from the ROM the self.pcreg. I don't think we want to do this anymore. We actually want to query the memory owner. So the problem here is that instead of specifically referencing the ROM, which exists in its own address space, we actually want to start referring to everything in the global CPU address space. So let's start doing that. And so now when we say, get me the instruction at 0xC000, we want to find out who's the memory owner of that, which we know is going to be the ROM at the moment, but we should get that value back. And then we just want to query the ROM as if it was any other bit of memory. So we just want to get the current byte of the PC is going to be self.get the memory owner of the PC reg. Cool. We want to turn the instruction into a byte, the byte into an instruction, yep. Unresolved right. So we get a memory owner back, and then we want to get at the position of self.pcreg as well. Yeah, okay. So this get, oh shit, yeah, this is why we did it differently, because ROMs are going to return bytes. Oh well, it's one of those things where you remember why you did something. We still want to load the values into memories, we just want it to return something different. Alright. And we can still add it to the memory owners, because it still defines get and get memory and stuff, all the things that memory owners do. Cool, so now when we say get memory owner self.pcreg, get pcreg, this should actually return a byte. So let's try that out. Let's get rid of all this crap. So what's our identifier byte? Is an empty byte. Cool. So this is probably wrong, so let's find out why. So we're going to know that the memory owner at the PC reg is the ROM, which is good. And then when we say get at the PC reg, it's going to return blank because we don't have the offset done. Yeah, so we need to do this. We need to offset our starting position. So there we go. So we want to go from our position to our end position. Now, what I really want to do is override this get function to return a byte. No, doesn't really matter. We'll come back to that later at some point when we want to do proper typing. Alright, so do we get a byte back now? We do. And if we convert that into decimal, that's 105. Now, what ROM are we loading in? Super Mario Brothers. Cool, so we want to load in this 7/8 in binary. So we're going to open up Sublime, we're going to look at the ROM, we're going to see what value we're meant to be loading in. Tools, packages, hex view. Oh, no, that didn't work. There we go. So we should be loading in value 7/8, which should be 120. Unless I'm wrong. Alright. So what we're saying is we've loaded the PC reg to be this, which is meant to be where our ROM begins. So this is what we haven't done. We haven't made our memory wrap around and start from 0. So we actually want to copy it. We want it to start at 0x8. We also want it to start at, so the ROM memory is going to be duplicated. Around 0xC000. So what that means is that get position and 0xC000. So we want to check here if it's greater than 0xC000, and if it is, we just want to minus 0x4000 from the address to get it back down to that 8000 address space. So if position is greater than or equal to, then position minus equals. Now we probably shouldn't do this unless this position, because we probably don't want this to be modified. So we'll create a new thing. Wrap position equals position. Actually, probably ints are passed in by type, not by, by value, not by reference. They should be fine. So position is going to be minus equals 0x4000. So basically what we're saying here is that if our position is, if we look at the memory map, since we're duplicating here, everything that is C000 or above is actually going to be the equivalent of 8000. And since there's a 4000 difference, we're just going to minus 4000 anytime we get something above C000. That's going to make our life a little bit easier. So now when we rerun this and we set this to 0xC000, it should return x, which should be 120. 120. Cool. So we're reading in our bytes again. And we can see that the x is over here. Nice. So we're back. We're back to where we were last time I worked on this, which is always good. So I actually do want to make this ROM object a memory owner. But I do want it to return a byte. And since it's wrapped, it's going to have to overwrite this get position, and it's also going to return bytes instead. But apart from that, it's going to behave functionally equivalent. It's going to have a memory start location, a memory end location. It's going to have to get some memory, get and set. Yeah, that's fine. And then we could probably just overwrite the set to raise an exception. Can't set read-only memory. It's probably going to come in handy later if we try to do that accidentally. Cool. So now a memory owner. Let's just say that this doesn't return an int. Yeah. Okay. I'll get rid of that error. Okay. So now we're getting in our first instruction. We want to get the data bytes for the instruction. So let's see that all our existing code is working. Instruction not found, 78. Rock on. So instructions.get identifier byte. Instructions. What are our instructions? Instructions are an empty dictionary. Right, because I no longer fill up this. So I tried to be kind of smart about this and use a use something to register these instructions, but I must have, oh no, register. I guess by moving them to a different file, this thing no longer works. So we're going to do it in a different way. We're just going to delete that. What we're actually going to do is something really interesting. I want to see if, because these all inherit from instruction at its core, so LDA inherits from instruction, everything inherits from instruction. So let's see if we can get a list of classes that inherit from instruction. And then that way we can kind of see what kind of instructions exist. So let's look at the instruction class. We actually don't have access to it here. So I'm going to say from instructions import instruction. It's actually from something called generic instruction. Name instructions is not defined. Right, okay. So let's say instructions equals 1 for now. Let's get down to this breakpoint. Cool. So if we look at instructions, instructions is a class. And we kind of want to know what classes inherit from instruction. So let's try and see what we can do there. So I believe there's something that gives us what things inherit from this, but I'll have to look it up. Not the MRO. Subclasses. It seems promising. Nope. Okay. So let's look it up. So Python 3 find subclass. So a lot of this stuff as we're going on we'll figure out stuff, how we can do things. New style classes have a subclasses method which returns the following classes. There's foo. Right, so we can call foo.subclasses as a method and it should return some stuff. Or inspect. It's interesting. Instructions.subclasses doesn't seem to be working. What if I inherit from this class here? Will this now return me something? Yeah, so we do get one thing that inherits from it, whereas this, which happens in a different file, does inherit from instruction, but isn't being registered. Interesting. Alright, for now, let's just do it. We'll come back to how we can make this, but so what are our instructions? Everything that exists in this file, every class that exists in this file. inspect dot get members of my module. So if I import instruction, this really should be called instructions. Then I should be able to do inspect.getMembers from instruction. Instructions. Cool. So now when I come to here, register is not allowed. Alright, I'll remove that from here. This method should actually return us, yeah, nice, a list of instructions. Class tuple dot name. Can I access this kind of stuff? Tuple object. Predicate. Inspect.isClass and is subclass. Yeah, so interesting. If you want subclasses, you'll have to recurse. So the problem is that they're in a different module, which means they're not being listed in the subclasses thing. So using eval instead of vars will make it work with any accessible class, not only those defined in the current scope. Nice. Right, so if I do of instruction, let's see if I can get, there we go. Now we've got all subclasses of instruction. Nice. And now we actually only want to get ones that define and identify a byte, and we also want to get all subclasses, because that means we know that they're a real thing. If you want subclasses, you'll have to recurse. Cool. So let's get a function that finds all instructions. And we're actually going to want to make this do for each subclass, and then for G for S in instructions. Right, so we're actually going to have to make it recurse. Self.find instructions. and it's a class. And what does it get passed in? It gets passed in the class. Okay. Cool. So we actually want to call this instructions here. So instructions are going to be self dot find the instructions for the instruction class. Cool. Now we also want to return my subclasses and this for every subclass. So we actually want to take this subclasses thing and we want to filter them and make sure that they return what we want. So let's do that. Now this was suggested in here. I believe doing some kind of functionality. Well, we just basically want to do a filter. Yeah. So we can just, alright, let's do it then. So, subclasses, and we'll do a list comprehension here, because why not? Equals a sub C. So for every class in the subclass, if subclass dot identifier byte is not none. And then basically we want to just return the subclasses that pass that, and for every subclass in any subclass, return that. Yeah, okay. So let's see if this returns all our instructions that we expect. So it returns CLD, LDA0 page, yep. So it returns 12 instructions in total, or 13, which I believe is the amount of instructions that we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Perfect. That is all our instructions. Now we don't need to class. Why is this giving me a instruction doesn't have an expected attribute subclass. It does. But maybe if I do that, that'll oh, okay. Oh well. Instructions for class list. Yeah, so this is actually going to return a list. And what we want it to return is a dictionary where it maps everything. Right, okay. So we want it to, so this is going to return a list. We actually want it to return a turn this into a dictionary. So instructions is going to equal a dictionary. Alright. So for every instruction in the list, we just want to add it to the dictionary. So add the identifier byte and then make it point to itself. Cool, so now when we look at instructions, instructions should be a dictionary, has 13 entries where the bytes map to the appropriate class. Yeah, which it appears that it is doing that. Cool. So we've now got all the things we need. Let's keep going. Roll. So we were talking last time about doing the fact that each of these instructions actually, whatever, they're pretty simple to do. You just need to map this and then make up what it is. So let's keep going on that. And to be honest, let's load in the test ROM and let's see what happens. So we're going to load in the test ROM. So the test ROM is going to have the same subject. This data here is going to be start being indexed at 0xc. So the first byte that we get in should be 4c, which equates to 76 in binary. Yeah. Shadow's name instruction from outer scope. Well, let's get rid of that then. Cool. So let's find out what it gives us. So what's the identifier byte that we get in? The identifier byte that we get in hex, or in binary, sorry, is 76. Actually, can I do just hex? Yeah, is 4c, which is what we expect. So we've loaded this into this test ROM into memory correctly, and we're now reading in the first byte. So what's a 4c instruction? So we go back to our map of what are all the instructions on a 6502 CPU. Well, let's just go, and I quite like the one on the Wikipedia page. Just as a quick reference. So, assembly language. Cool. So we're looking for the instruction 4c. So a 4c is a jump absolute. So we need to be able to implement a jump absolute function, which we have not done. We have implemented absolute addressing, so we can reuse absolute addressing, which is really cool. And so absolute addressing means that it's going to give us a full address, which is going to be 2 bytes long, and we're going to use those bytes to jump to that actual location. So let's do that. So let's implement, let's go to base instructions. So we've got LDA, LDX, LDY, store A's, set bits, so on. What we actually want now is a jump instruction. So it's going to inherit from instruction. Now what do we need to overwrite? What's a jump method actually going to do? It's going to get a memory address, so that'll be handled by the addressing. It's going to get a value from that memory address. So this get data function probably doesn't need to do anything. It's just gonna pass. It's going to write. It's not going to do anything on the write, and it's going to apply the side effects. So the side effects will probably just be jumping to the memory address that it gets. So let's make it override the side effects function. And it's going to do cpu.pcreg equals a value. Now, interestingly enough, it's actually going to pass in the value. So actually, we kind of want to override the write function, because that way it will get passed in the memory address, and it's actually writing the PC reg. So it is doing a write. So it's going to write the CPU reg. So cpu.pcreg is going to equal the value that we found at that memory address. Or is it going to equal the memory address? Alright, we'll figure that out. Yeah, we want to jump to the memory address that is given in the instruction, instead of reading it and reading the value there. Let's keep going then. So what's up next? So we've got an instruction. we've now got a jump instruction that does what we want. So now let's make jump instructions. So let's make a jump absolute, which is what the 4C is going to be. So it's going to use absolute addressing, and it's going to use a jump instruction. And the identifier byte that we're going to use is going to be the bytes of 0x4C. 4C. C, I believe. Yeah. So the memory address that we get back should be these next two bytes, which is F5C5. But since it's in little endian mode, which means that this byte and this byte are going to be flipped when we read them in, it should be we want to be jumping to the memory location C5, F5, unless I'm mistaken. So let's see what happens when we do that. So this instruction should now exist, and it should be loaded in automatically. It's not found. That's fair enough. So why isn't it found? So let's look at our instructions. Instructions are not being loaded in. We need to do, wait, what? Class.subclasses. What we discovered back here was that you actually need to call eval foo to get the global namespace. Eval instruction. Right. So if we come in here, what does an eval instruction actually give us? What is this class? It is a class. Okay. So subclasses equals I get the name of the class? Yeah. So subclasses equals subclasses. If the identifier byte is not none, and we actually want this to be eval of the subclass dot name. Yeah. And now when we return the subclasses, we want to iterate through for this, for G and soft-defined instructions, G for S and class. Oh good. What happens if we run this? See what instructions returns. Instructions is empty. Alright. Well, let's send the debugger in and see what happens. So what is subclasses going to equal? Subclass is going to equal an empty list. So class.subclasses is empty. Whereas eval instruction dot subclasses So now I'm confused, which is always good. So eval instruction should return the instruction class. So eval instruction dot subclasses. I see what's happened. I've missed an underscore. It's going to be empty. I would swear that this was working before. Yeah. Different modules. Let's look up if there's a better way to do this. So let's start off going back to basics. So we're down here. We want to eval instruction. We want to find the subclasses of instruction, which currently is returning an empty list, even though instruction dot subclasses is also an empty list. That's odd. If I change something here? No. So jump. The identifier byte. Huh. I would swear that this was working before, which is always a good thing to happen. The problem here is probably going to be to do with the fact that I'm pushing this into a function. I was getting back a list of instructions before, was I not? Have I changed something somewhere else? So it's always good to come back to kind of a source tree or something and see what you've changed. So we've added the jump instruction. That probably shouldn't do anything. We have found the instruction. Yep, sure. Nope, nothing crazy there. We've made instruction inherit from object. Wouldn't that be funny if that was what was breaking everything? Nope. Okay. Well, that's always nice then. So interestingly, instruction. You know what it is? I bet it's going to be something to do with import order. So if we do import instructions, so we're going to have to import all the classes. Oh god. So we don't need to do this eval stuff, we just need to import. Okay, so the way Python is going to be doing it then is that this import instruction is actually going to be running the code in that class and registering anything. So we actually need to import instructions as instruct instructions file, and then we need to do this so it registers all the instructions first before we can find out what's in the subclasses. Right. So this should just be instruction. Okay, so this should work now. So we should get back a thing of instructions. Man, that was weird. So what was causing that? So I can figure that out. So the problem that we're running into was that by not importing those files, since it's not a compiled language, the Python interpreter can't know about those classes until it has imported those files and run over those lines. So by removing that import before, which was probably a bad move, it was meaning that I couldn't see those classes. Bug detected. Alright, cool. So now we should have a 4C somewhere in here. Yep, jump absolute. This BL is the binary, the ASCII representation of 4C. So we can see it up here in the hex view. So we know that that's right. Cool. So let's see what happens. So the data bytes that we get back from a jump instruction should be the next 2 bytes, so it should be F5 C5, but it should be flipped. Was it flipped yet? Maybe not. So the data bytes are F5 C5. Yep, so we're just reading the raw data out of the file, and then we're going to execute the function. Alright, so let's see what happens. So we want the memory address. The memory address is going to be absolute, and therefore it's going to be the absolute address of C5F5 because it's in little endian mode. So we should get back a thing that says C5F5. So what's our memory address is going to be an int, and if we did 0xC5F5, this should equal the same thing, which it does. So we are getting our memory address back correctly. The value that the a jump instruction is going to write is going to be nothing. None, yep. And the write function, it should write the PC reg to be the memory address. The memory address being 0xC5F5. Yep, that seems right, and then it shouldn't apply any side effects. So now our PC reg, what's our PC reg? Is going to be 5067, is going to be C5F5. Now the real question is, do we need to increment here, this PC reg, or does it want us to start execution at that point? So that I do not know, and that's going to depend on how jump instructions work. So let's look up 605 instructions. Now, there's a really good site called Skildrick Easy 6502, which is what we're going to be using. So let's look up jump. Jump dereferences to CZ0. Yeah. Jump. So the jump instruction causes the process to look up the 2 bytes at F0 and F1, put them together to form the C01. I'll talk more about jumping in the section on jumping. So jumps are not conditionally executed, and second, they take a 2 byte absolute address. Cool. So if we do a hex dump of this, a disassemble dump. So basically, the disassembly is that we should jump to 0608, and then the next execution thing should start at 0x08. Right, so after we do a jump, we don't want to increment the program counter. We just want to start executing from that point. Okay. So if we have not done a jump. So probably the easiest way of checking this is just going to be saying if self.pcreg is equal to what the PC reg was at the start. So we're just going to store up here when we get our PC reg, get the current byte at PC. So and then if our PC reg gets incremented, doesn't get incremented, then we want to increment it ourselves. But if it has been incremented, then we don't want to do that. So here, what is our self.PC reg? 50667. What was our starting PC reg? Was 49152. So we have done a jump, and therefore this will equate to false, which means that we will not increment our PC reg. Awesome. So our jump operation should hypothetically work. Alright, so let's see what happens when we get our next byte. So what was the instruction that we just got in? LDXIMM. So, and where are we pointing to? So let's figure out and just verify that we're getting the right memory location. So what this is saying is 4C F5 C5. So it's saying to jump to memory location C5 F5. The memory location C5 F5 is because everything is set offset. God, this is where it's going to get a little bit mathsy, but hey, Dan Tup, welcome. Thank you for some of the feedback. The NES test run. Wouldn't it be simpler, cleaner to increase the PC at the start as you read the values? Then you don't need to do anything here. Yeah, that's true, and then we can just override it. Yeah, because the only thing that's going to happen to the PC reg is it's going to get updated. You are correct. So instead of doing that, we can just increment the PC reg. And so if it gets overwritten from anywhere here on, then we don't really care. Oh, you need to know what the instruction is. Whatever. It'll just get overwritten. So we just have to do it before... Oh, no, PC reg +1. So we just have to do it before we execute, but after everything else. Okay. Yeah, so... Hey, Danny. Yeah, I've been reading your stuff and putting in the NES test ROM. I think I understand everything you're saying, but basically I've written it like you have, which is instead of writing it twice, I just have a mapper, but I'm mapping it twice and just doing a God, where is it? In my ROM, just doing an offset. So if it's greater than a certain position, I'm just going to mirror it. Hopefully that'll work. Yeah, NES test. Let's keep going then. So we have a jump operation going. That was pretty easy. And the next operation is a... Let's see what the next operation is. So we start with the jump, and then we've got an LDX immediate. So what we're going to start doing now is comparing to the log output. So we start at C0, we get that, and then the next instruction should be a load X immediate, which it is. So we're in the right place. So what we're going to start doing is start doing some output like this test ROM. And yeah, see what happens. Alright, so yeah, that makes sense. Yours does the same now. Yeah, that makes sense. Yeah, sweet. Glad you could come and catch a bit of it, but yeah, you have been leaving some really helpful comments, so thanks for that. That's awesome. I was just saying people should go check out your Chip 8 thing, because I read that blog post and it was pretty cool. Obviously a bit simpler than the NES one that we appear to be both doing, but I think probably better start if you're looking to get into emulation. Although I've jumped straight to this, and this is kind of fun. So what are we doing now? So we want to format all the instructions so they print out like this. So let's go to our instruction class and let's overwrite the print function. Oh, we already have overwritten the print function. Cool. So let's give an example of what it should be. So we want it to print out what is the PC reg. So it should be PC reg. The bytes of the instruction, the name of the command, the address that we get back, and then the status of our registers. I started the NES 2, just got stuck on the PPUs and needed an instruction. Yeah, I haven't been thinking much about the PPU or the APU, to be honest. But yeah, I anticipate that they're probably not going to be that fun. I think all I know about them is it's using like sprite buffers and stuff like that so you can kind of push sprite patterns onto it and then like blit them at a point. But to be honest, that is like the only thing I know. So it's going to be fun when I get to it and have to try and figure that out. Alright, so let's go. So we actually want it to be PC reg. The bytes, our name, the address, the register, some spaces, and then our registers. So let's do that. So we want the first one to be the PC reg. Now this is going to be interesting because we need information here about the PC reg, the bytes, the name, the address. So potentially we don't know the value of the PC reg, we should just print out this information, and then the CPU can print out the PC reg and the register information. So let's just make this instruction print out about itself. So just print out what were the bytes that I got in. No, it doesn't even know that. The CPU knows that. So what's my name? Oh, yeah. Funky. Interesting. What's my name? Probably it should just print out its name. And then everything else is actually the address value. Interesting. Anyway, for now, let's just make it print out its name. I'll just wait until you get there and then copy. That's the spirit. I think it's good someone else is doing something similar. It's kind of fun. And to be honest, I would never have got that NES test thing working unless I understood. You post that comment, I understood what was actually going on. And it's good, it seems to be working now, so thank you. Now, the instruction, right. So before we execute the instruction, we kind of want to be doing at the thing what is. So I want to say what is our PC reg? What's the bytes? What's the instruction? And what's the status of everything before we execute? So let's do it once we've found out what kind of instruction it is. We've got the data bytes. Let's do it before we increment the PC reg. So print out diagnostic. Cool. And we know which format that's going to be in. Now, if we just do print instruction, this will call the .string method of that. So let's go to here, and the first thing should just print out that we're printing out a jump instruction. That didn't work. Oh, I guess I've got to maybe cast it to a string. Hey. That still didn't work. That's interesting. Class.name. Huh. That shouldn't be a class method. Wait, it should be a class method? Can you overwrite string as a class method? What happens if I do this? Where does this go? Huh. Class instruction. What if I said? Yeah, okay. So what is instruction? So instruction is a class. We actually want to overwrite the string class method. Now, is that possible to do? Let's find out. Some of the stuff in the log is complicated to log, e.g. the bit in the middle, jump, xxx, so I just skipped it and compared the first 3 columns and the registers at the end, ignoring cycle scan lines. Maybe easier how you're doing it. I subclass CPU as logging CPU and dump the bytes as they got read. That's an interesting point. I mean, the CPU should have access to all this information, right? I mean, the CPU definitely knows its PC reg. It definitely knows the bytes that it's reading in. It knows the type of instruction from what it tells it. And to be honest, it can get the, if I really wanted it to, it could just call the get address from the instruction, and it would return what that value was. So I could log that bit, and then it knows the value of the registers. But you're probably right. I probably don't need it to do that. I mean, there's no harm in doing that, I think, if I can figure out how to do it. But since I'm doing it in the CPU, it should be a bit easier. It does have access, so I was trying to keep logging out of in my test class. It was a bad idea. Yeah, maybe. Might be a bad idea. Might not be. I think, ideally I'd like to take it out, obviously, but for now I'll just, path of least resistance until it gets a bit out of control. So can you, alright, Python, string of, okay, so we want to know if we can overwrite the string method of class, of a Python class. That's what I'm trying to say. Let's see. Types are just objects, so they're converted to string by calling string on their type, which is the meta class. You have to override the string method on their meta class. Yeah, huh. Python 3, because I think Python 3 it seems like it's changed this kind of stuff. Whoop. At the time I wrote, the current development version had changed the result of string some type to simply sometype.name. Oh, so maybe I can just override the .name method. Ah, I don't need to override the .name method. Screw that, alright. So if I call instruction dot name, yeah, jump absolute. Nice. Okay. Now we're cooking. So we want to format the name. Where was that format that we wanted? Yeah. This is my example. So C00 is the PC reg. 4CF5 C5, those are our bytes. Data bytes. Jump is the name of the thing that we've got. We'll come back to this address. So let's see if that prints out the correct thing. So it should print out 49152. So we should turn that into hex. Oh, is hex not a thing you can do on ints? 123.hex. No, okay, so you can do hex number. So we want the hex of this. We want the data bytes. So F5, C5. Now it would be nice if we turn that into hex. So databytes.hex. And instruction.name. Alright, let's check that out. Okay, so 0xC000, correct? F5, C5. Oh, we also want the instruction. Okay. So we don't just want the data bytes, we want the instruction byte as well, which is the identifier byte. So identifier byte plus the data bytes to hex, and then the name, which is jump absolute. So 4C, F5, C5. Oops, I've got the format right here. So C000 matches up. 4C, F5, C5, correct. Jump absolute. Yep. C5, F5 is the address that we actually want it to go to. And that $sign is going to be interesting. So this is going to... Yeah, okay. Let's just say it's a jump absolute. And then we want to print out the value of the registers. Alright, so what are the registers? So let's get our A register in there. So self.areg, and then so A is going to go to that. X should point to a register. What else? Y, the Y register. The P register, which is actually just called our status reg. Now I believe status reg is of a type status, which has all these bits. So I'm going to define a string method on this that's going to return binary number. So how do we turn a binary number into an integer? Int dot from bytes. Yeah, it's going to be interesting, isn't it? I could just like bit shift this or something. Good. So we want the... Alright, let's just check out what happens when we do this. We'll say it returns some bits. That's our Y register. Our P register is going to equal something. And our stack pointer register, as well as cycle. So I don't know what cycle is going to do for now, but we'll figure that out. This should be self.stack pointer. Cool. Bam, bam. It's really looks terrible. Oh well. Alright. So we should get something for now. Self.string return non-dict. Okay, yeah. So what is bits? So bits is a dictionary. I probably actually want to make this an ordered dictionary. And so that way I can guarantee the order of it. Ordered dictionary. And that's probably going to make my life a little bit easier. Now we're going to do this. Now I believe that's not going to guarantee me order because I'm passing in a non-ordered dictionary to it. So if I go like the dot items 0. Ah, you kidding me? Okay, give me the next. That's turning me. Odict items is not an iterator. Okay. Anyway, I believe you have to pass it a list, and then these should just be passed in as tuples in that list. Alright, so let's just get rid of them. Let's add these things to the start. Then we're going to find these, and we're going to replace them with commas. And we need to add a comma at the end of every line, which we can do like this. Now, let's just reformat that code and make it look nice. So now, when we do this, it should, self.bits should be an ordered dictionary. Yes, which it is. Sweet. Carry interrupts. So now we actually want to return this as a binary value. Jeez. So for bit in self.bits.items, We actually only really care about the values. Can you enumerate over these values? Probably. So I bit. So let's start off with 0, and then for every bit, we actually just want to do value should be the value of the bit. So the bit, turn that into an int, because we're going to be casting a bool to an int, so either a 1 or a 0. And then we're just going to need to times it by its index. But let's see what happens if I do this. So our thing is actually, should be 1 there, 1 there. I think it should be 34. 24. Huh. I swear it started at 34. That's probably not good. What's 24 in binary? 0x B for binary. So 0. So 1, 2, 4, 8, 16, 8. That's 24, right? What did I say mine was? 32. Which is 0, 0, 1, 0, 1, 1. Nope. False, false, true, false, true, true. No. Alright, this is where things get a bit sketchy. So let's go back to our the NES wiki. And we're going to try and find up the startup state. I skipped the shifting and just cheated like this. Internal byte get status, return byte, negative overflow. Yeah, exactly. I'm hoping by doing an ordered dictionary, I should just be able to do this and then times it by like that. Or, I mean, like, you know, to the power of I or something. I think that's to the power of. And then that way, this should return the same thing as that, and I don't have to, because I've already ordered it in my dictionary, I won't have to do anything. Maybe. Wait a minute, this isn't what I was thinking. Where is the NES wiki? NES dev wiki. Makes sense. Yeah, I think I might just have the wrong initial status. NES reference guide. Is there like a startup thing? CPU. Startup state. Yours was just bools, not an array dict, so I can, yeah. That makes sense. I think this way should be easier. But since I have it in this. The golden log test of NES differs with this in the irrelevant bits 5 and 4 of P. That makes a lot of sense. So let's just set 5 and 4 to be false. And it says that it starts at 24. So 24 to binary. I'm so confused. Whereas, oh, is this in hex? Oh, 34 hex to binary. Oh my god. Okay. 34. So this is saying the third bit is enabled, whereas 24, yeah, okay. So 24 is just this 1, 2, 4, 16, 4, 8, 16, 32. So it's saying that this is still true. I believe. So this is going to be 0x 0 0 0 1 0 1 0 0 should be 24. Oops, B. Oh, Python, you hurt me. Oh, I'm so off by 1 in every regard. 0 0 1 0 0 1. It's the high one. Okay. Am I crazy? What am I doing here? Equals 36. Whoa. Oh, because this is giving it to me an int. Oh, God. Okay. Losing my mind. I gotta shoot. Gotta be at work. That's fair enough. Yeah, I'll keep going. Yeah, keep leaving comments, whatever. I'll catch you next time. Next time I'm around, hopefully. Good luck with your the PPU when you get back to it. Cheers, Danny. Right, so this is going to be difficult because I am not smart. Alright. So we start at 34 in hex. And the golden state of the PP of the thing says we should start at 24. So let's set it to be that. 0 0 hex 24, which is this. So if I do this from the bottom up, so 0 0 1 0 0, false, true. So value should equal 24, which it does not. Int bit I. Well, let's do this. So the first thing should equal 0. Yeah, okay, so that's not the power operation. Math.power, power of I. Let's import math. So bit should be int bit should equal 0. And then how does that work? Math.power int bit to the power of 2. What the hell? Oh, okay, so we're raising 0 to the power of 0. Will do. See you, Danny. Cheers. Let's keep going though. The 0th power of 0 is equal to 1, which we probably don't want. Okay. So let's go back 0, 0, and this next one, our interrupt bit, oh god, how am I doing this? Why am I doing this wrong? It should be 2 to the power, so it should be this times 2 to the power. And when we start, this should be 2, no, this should be 1. So now it should equal 4 times the interrupt bit. Yeah, perfect. So this should now return the correct value of 24. But it's 36, but 0x24 should be 36. Okay. So we get the value back as an integer, and we just want to return that as hex. Well, we can stringify that. Let's just check that that returns actually what we want. Float object. Holy crap. Okay, 0x24. There we go. That's a lot of casting around, hey? Nice, so we now get what's our status bit. So, let's go. What do we print out? So we start at 0xC000, yep. The data we get in is 4CF5C5. It's a jump absolute. All our registers are set to 0. Our P is set to 24. SP is set to, well, we probably want to make that a hex value as well. Actually, we'll just make this hex as the status reg. Then that way the status reg can just return value, int value. So now it's an int. Cool. Where was I doing this? And there we go. Hex of the, oh shit. Hex dot to int. So we'll make that override the string method. Alright, yeah, P equals that, and this is at FD, which is what we wanted. And then the cycle stuff we'll ignore for now. Alright, let's keep going then. So the next instruction. So let's put this over here, and let's start comparing instruction to instruction. Oh good, there we go. Nope, boom. So let's put that over here. So we start at C00, 4C, F5C5, jump absolute, all our things are correct. The next thing we are execute the instruction at 0C5F5, A200, yep. It should be a load immediate. All the values are still set to the same thing. Traceback instruction not found. Excellent. So what is the instruction? 8.6, which is what we see here, which we know is going to be a store X, but since we haven't implemented that, we're going to need to do that. So let's go through and let's implement some more instructions because we know they're going to come up. So we've got load A, we've got load that, we've got store A. We just need more things. Alright. So we've got store A. So let's get store X and then store Y. So the A reg, the X reg, and the Y reg. And we've got load A, load X, load Y. Cool. Now the instructions. So here's the interesting part. So we have something that defines load A indirects. Yeah. These aren't that verbose actually. I guess I'll just do them. So what do we want? What was this thing? It was a store X. So we've got a store A, but not a store X. So store X, absolute, so on, so on, so on. So I kind of want to automate spitting out these different types of addressing, which is kind of boring and to construct these classes, but at some point that gets a little bit dodgy. So we're going to do some nice copy pasting. I'm actually going to do this in Sublime, like where all code goes today. So we've got all our load A classes. So let's find all load A's. Let's replace them with store X. And that should do it. So let's put in our store X's here. So we should import store X. And we're going to need to change all these bytes around. So let's change them all to 0 for now. And then let's find them all on the chart. Now, ooh, where is my browser? Over here. So how do we do that? Where's the things of all that? Charts are in here somewhere. So let's make this full screen. Let's find all our instructions. Now there are a couple of other sites that list this. I wonder if any of them have better ways of displaying this information. E-Tradition 6502. Cool. Yeah, that looks pretty good. This one's got more detail, but I don't actually know. Ah, this is... Oh no, it's not. Oh no, StoreX. Yeah, so there should only be... So what we're saying is there should only be 3 StoreX's here. There are only. Nice. And this is actually going to tell us which ones those are. So 0 page Y, and absolute. Alright, so let's put them in. So we actually only need 0 page Y, and absolute. So that can go. 0 page we need. 0 page X we don't need. But we do need 0 page Y. Right? We need 0 page Y, and absolute. Absolute. So this is all the store X we need. Alright. Load X. Load what? What are the bytes that we need in these? So 0 page is 86. Zero page Y is 96. And 0 page absolute is 88. Cool. So now, when we run this, we should get one step further before we hit an instruction that we don't know. Oh, we should get many steps further. Right. Okay. Yeah, so we're doing a lot of store X's here. So again, to compare this, we should be executing F7, F9, FB, and we should be storing X, 8X00, yep, 10, yada yada, store X, so they're all 0 page things, and we can see that so we want to store X, right, and the value of X is 0, so we're storing the value 0 at the memory location 0. We're storing the value of 0 at the memory location 0, 0, 1, 0, and 1, 1. So how do we verify that that's what we're actually doing? Well, let's open up the storex instruction. And it comes from a storex. So anytime we do a storex, let's take a look at what it's doing. So it writes to memory, and it's going to get the data. So when we get the memory address back, the memory address is 0. The value that we're going to write is 0. Are we actually going to do any writing? Who's the memory owner of that? Is the RAM. So we're setting 0 to 0, which is in the RAM. Okay, that seems around right to me. And if I look at this, 0 to 800 is the RAM. Okay, so let's keep going to the next instruction. The memory address is 16, and we want to be writing 0 to the RAM at memory address 16. Yep, okay. So on and so forth. Okay, well that worked perfectly. Alright, so what was the next instruction that we have to implement that we don't have? Instruction not found, 20. It's going to be a JSR. So let's find JSR, find out what JSR is and implement it. Jump to subroutine. So JSR pushes the address of the next operation onto the stack. Do I still have the skill trick? That's a nice one to have open. Boom, 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 boom. JSR. Jump to subroutine. And jump from subroutine. So JSR is used to jump from the current location to another part of the code. RTS returns to the previous. Basically like calling a function and returning. Okay? The processor knows where to return to because JSR pushes the address -1 of the next instruction onto the stack before jumping to a given location. The RTS pops this location, adds 1 and jumps to it. Right, so these are just jump and then jump back things. So like you do when you're going into a function. And you just chuck them on the heap. Chuck them on the heap? Onto the stack. Okay. So we're going to chuck some things onto the stack. First instruction causes execution to return to the init label. This sets the load, returns, then it'll go to loop. It'll come back here until, yeah. Okay. So how does JSR actually do it then? It only has an absolute mode, which is going to be hex 20. So our base instruction is going to be class JSR. So what's the JSR instruction going to do? It's going to jump and it's going to write to the stack. Pushes the address -1 of the next operation onto the stack before transferring program control to the following address. So let's look at instruction. Let's see what a jump. So it's gonna jump. So we know that. So it's gonna change the PC reg to the instruction of that. So it's very much like a jump. What is it also gonna do though? It is also going to push the address -1 of the next instruction onto the stack before jumping to the given location. So it's going to write the value to the stack. So if we look over here, JSR should write a value to the stack. So the stack pointer is now FB. So a value has been written to the stack. Yeah. Okay. Then how do we find the stack? Who stores the stack? So the stack is, we go through the stack pointer, which is owned by the CPU. So I'm just going to do this. JSR, for the moment we're just going to make it a jump instruction. And then up here, JSR. So absolute is the only thing that it uses. And its hex is 20. So it uses absolute addressing. It comes from a JSR command. And the identifier byte is going to be 0x20. Alright. So now it should exist, and it should hit down here onto this JSR method, which it does. So what's the memory address that we're going to? Let's just put that in hex. C7 2D. Does that line up with what we expect? Jump to C7 2D. We also want to write our value of the current program counter onto the stack. Okay, so what's the current program counter gonna be? Well, we've got the CPU, so we want to write the PC reg. But before we write it, we want to store the PC reg on the stack. And then update. So actually this can just inherit from jump. And then can just jump by using the using all this crap. Yeah, okay. So we're gonna, this will just jump. Jump to the memory location. Store the PC reg on the stack. So where's the stack? So CPU.spreg. So this is the stack pointer register, which is a hex value. So what do we actually want to be doing? We want to update the stack pointer register, but we also want to write to whatever the current stack pointer register is. So how do we write a value? We use writes to mem, and then that will do this. So we actually want to get the memory owner of the memory address, but the memory address isn't this memory address. The memory address we want to write at is the CPU.PCReg. And then we want to set the CPU.PCReg to the value of the PCReg, so the CPU.PCReg. And then once we've done that, we actually just want to update the PCReg, the SPReg, to account for that. And how much do we need to increment it? Pushes 1 before transferring program control, and the address is going to be 2 bytes big, I believe. Yeah. So plus equals 2. Alright, so let's see what happens when we do this. This is going to get real interesting. So who is the memory owner? So the memory owner is the ROM. Yeah, that's true. We don't, sorry, this should be the SPReg that we want to write to. And then we actually want to set the SPReg to be equal to the PCReg. Set the memory at SPReg. Okay. So who's the memory owner? RAM. That seems much better. And what's the CPU.spreg? Let's just view that in hex, because that's always a good way to do it. 0xFD. FD? Yep. FD. Cool. And then the stack is actually going to get smaller. Okay. Yep. And then we want to set that value. So let's see what happens. Let's see who this goes to. Set. So who? This is the RAM. So if we self.getMemory, and it's a list. So let's see what happens. What is this memory location? What's in there currently? It's 0. And what's the position? It's at 253, which in hex is FD. Yeah, so the memory location at FD is currently set to 0, and we are setting it to value. Now what is value? Hex is value. Right, so we actually want to set the next 2 bytes. Oh geez. So depending on how, we sometimes we want to store 2-byte values, not just 1-byte values. That's kind of interesting. Alright. Well, let's say that it's just going to write sets int at given position. Now we actually, it's like self.getMemory this is actually just going to return a single int. But what we're saying is when we are writing, instead of setting this value to something that's larger than a, how do I say this, that is larger than a byte, we can't have it be larger than a byte. So if it's larger than a byte, it should just start overwriting values all the way down. And this value, yeah, this is where it's going to get interesting. I think I might cut it there. I don't think my brain's ready for this kind of contortion at the moment. I think this is going to need to be a minus, which increases the size of the stack. And we know it's actually going to write 2 bytes. Maybe we pass in how many bytes it writes. Okay, let's do that for now. And we'll say size is an int equal to 1. So for I in the range of size, then we want to set this minus size or plus size. If we start at FD, we actually want to be writing upwards, right? Ooh. Yeah, this is where it starts getting a bit tenuous. Let's see what happens if we do that. So, memory owner, we want to get at FD. And then we want to get at FC. Yeah, okay, so we've written 50,000 to both of them, when really we want the top one to be something and the bottom one to be 0. Well, to be something, but yeah. Alright, so instead of writing the value, we want to write the top bit of the value or the bottom bit of the value. So what does value equal here? Value 0, value 0, value 0. Value is 50,000, which is C600. So we actually want the bottom memory value to be C6 and the top memory value to be 00. Yeah, okay. So how do we get, so we've got a value. We can put that in a hex. Can we do bytes from value? That doesn't seem right. Right, okay, so we need a, if it's greater than 256, yeah. Might need to divide by 256 or something. Anyway. For another day. Alright, let's stage all this stuff up and add more instructions. And got NES test running. Alright. Committed. Perfect. I'm going to add a tag, which is going to be episode 5. And going to do a push. Which should work, and then that's probably what I'll do today. So coming back, we've got to realize that we're going to have to be able to write multiple positions to memory. We're going to have to figure out how to turn an int value into the correct amount of bytes and how we, do that. There's probably going to have to be some bit shifting involved. I'm just going to mess around with that for a second, but probably not going to commit anything here. So what was value? Yeah, let's wait until we get to the correct one. Let's photo value and shift that by 2. Oops, wrong way. Shift it that way by 2. So I want the first one to be 0. We want to shift it by 8, don't we? What is the hex of that? Yeah, so we want to shift it by the amount of bits, and then if we, for the second little bit, we actually want to do value bit shifted by 16, which should equal 0. So the memory, so in the first location, we want to write C6, and the second one we want to write 0, 0. Or maybe the other way around. This is going to depend on how we are writing things into memory. But either way, it's going to be value shifted by 8 times I. And if I turn that into hex, it's going to be 8 times I plus 1. Oh man, that's some bit shifting. It's going to be 0, and the next one should be 0. So value holy crap. Okay, so let's look at the hex of that value. So the first thing we write is 0C6, and then the next thing we write is 0, 0. So potentially we might need to flip the cardinality of this, but whatever. Figure that out next time. Alright, thanks for coming along and thanks for watching. I'll see you all.